possible because there's no answers. There's no errors. There's no general solution to this problem unless you place some conditions on this function. If this function is smooth enough, if this function is regular enough, then you can do something. But if arbitrary function, any model you want to build, you can't, because there's no restriction on how so-called data-driven or saturated the model can be. And without any errors, you cannot possibly say anything without the error, or because all you see is just residue. Once you fit the model to the full sample, everything you see, the discrepancy to this fit function is what we call residue. So here's very important to keep in mind two different things. What is residue? What is error? Error is genuine. Residue is proxy. Okay? Residue cannot be trusted. Error can be trusted. You must create error. The question is just how do you extrapolate those errors? So subsampling Robert acquisition is allow you to do that. And therefore, we can get the error on the bracketized predictor, but not the full sample predictor. It's not possible. And this is not an issue with design-based or model-based. This is just a general issue. Okay, so you go to the, I think recently there is a paper a couple of years ago in JASA discussing this issue from a model-based point of view. And the only thing you can get is that I will get the error of, if I'm doing sample size n, k-fold, what I can get is a sample size n divided by k times k minus 1. If I had a sample of this size and it's doing k minus 1 fold in that sample, that procedure, that estimate error I can get, but not what I actually get out. You see my point? It's exactly the same problem. Okay? It's because without placing any conditioning on the function, you need errors in order to assess the error. You cannot rely on residues. That's it. There's no general solution to that. Okay, so that's it. Having said all this, the most difficult problem we still don't know is how do you split? How do you do the Q design in some sense is optimal, right? This you only can do is empirically. You can try different schemes. You can get some ideas whether for this situation, some kind of split is not obviously unreasonable, okay? But there's no way you can, there's just no math ready yet. Maybe someone will find it in future, but at the moment, no math yet to tell you, given this problem, given this function you are building, given these are the data you see, what is the optimal split when you do this kind of cross-validation for either for error assessment or for building function and so on and so forth? What is the optimal split? We don't have that generally.
You say optimal or more robust?
50-50 is quite robust. 50-50 is quite robust, I think. But it's just, we don't know optimal. Giovanna.
So first of all, thank you for the whole session. Usually you find yourself like many instances like in the Groundhog Day movie in which you keep living over and over the same session in all conferences, and even all these many papers on probability, non-probability samples. You think you're reading always the same paper, which is the difference between non-probability sample and non-response. Sometimes you're reading the same paper in which just non-probability sample has replaced non-response. But here, finally, so thank you, Pierluigi, I've seen something different, so thank you. And you already replied to Elisabetta saying you cannot really use it to adjust estimates, but can you use that to at least, in a sense, test whether in your data you do have missing, not at random, just like looking at the corroboration picture from Lichun, whether your flat part it becomes to be too big, or maybe it's not that big, so maybe your data doesn't really have missing, not at random.
Well, I don't know. My impression is that, well, in my experience, the assumption say the sampling. Well, there are papers in the literature concerned with testing a sampling design is ignorable or is not ignorable. but there are two issues. First of all, they should be adapted to this case. In the second place, and even more importantly, this is a kind of post-testing inference, which is different from inference. You first observe the data, decide the sampling design is not informative, and then make inference. But in making inference, you should take into account that you have already tested your sampling design. So it's not so easy, I'm afraid. It's a sort of post-selection inference, which is a difficult task in statistics. It's similar to making inference on regression coefficients of a regression function, a regression, say, hyperplane, after having included in the sample with some methods the regressors. You can't use simple, for this, you can't use simple t-test. And for this reason, the sample is sometimes split, just to avoid this kind of complication. So maybe yes, but it should be studied. But it could be very promising.
I have the microphone for Brunero. So the exchangeability issue of the conformal prediction reminds me of the of all the issues in when you wanted to be purely Bayesian in a finite population inference, and so you cannot really go very far because of the exchangeability that collapses with without replacement designs. Can we learn something from that experience for adjusting the conformal prediction there?
Not so much, because the Bayesian theory itself is so limited that there is not so much to learn. Now here the exchangeability assumption is crucial because the value that you want to compare must be exchangeable with the others. So it will be one of the n+1 values in the bag of your residual, and exchangeability guarantees that the distribution over the n+1 position is uniform, and this is the only things that you need in order to provide the theorem, basically. And so you cannot escape from this assumption apart from the covariance shift methodology that I mentioned at the end. So by giving different weight, you have no longer a uniform distribution among the residual, but a weighted distribution of the n+1, and in that case, you can win the match.
So we have other questions, please. If yeah? Okay, then if there are no other questions, let's break for lunch. Thank all the speakers, please.